All right, so for number 5, determine the formula for the nth term. Okay, so the nth term of a geometric sequence. So the nth term is basically what is the T of n formula with everything except for n filled in. Okay, so let's go back to the text there. What is the nth term formula? Here it is right here. Right? So this is our formula that we're starting with. Okay, I'll just kind of throw this up here so we can see it. And so we want to have everything filled in that we can except for n. So that means I need T1, and that's pretty much it. But I also need what? Anything else? Oh yeah, R. I need R. Can't see it in there. But you need T1, and you need R. So let's take a look at C. That was the one that was asked about. So T1 is 5. Does that look good? Okay. Now R, oh sorry, that's T3. Sorry, I was looking at D. So T1 is not 5. So we have to hold off on that. But what we do know is that 1, 2, 3, this is 5, and then 4, 5, 6, this is 135. Does that make sense? So I can find out R the same way we did number 4. You can go 5 times R to the power of 1, 2, 3 has got to equal 135. So you know this is the situation with a geometric sequence. And so you can solve for R, and we'll do that. So R cubed is 135 divided by 5. So what's that going to be? 135 divided by 5. Anybody got that? 135 divided by 5. So 27. And the cube root of 27 is 3. So R is 3. Okay? R is 3. Now we need to find T1. Well, T1, again, you can set up another equation. T1, that would be this one, times R, right? So that's times R squared has got to equal 5. Well, we know R. So T1 times 3 squared equals 5. T1 is 5 divided by 9. 5/9. So I think we've got what we need. We've got R and we've got T1, and I think that's all we need to write an equation, correct? R, T1. So you go back there and you say T of n is going to be equal to 5/9 times 3 to the power of n minus 1. Does that look correct?
Mm-hmm.
Anybody that did that? You got that? Okay. So there is your, sorry?
90.
Okay. Any other questions about 5 though? Okay, so just going back, here's number 4 again. Right? We found R, found the ratio, and we're going to fill in the missing values. Okay, so those jumps, each multiplication is a factor of R. Okay, so let's do number 9 real quick here, or let's take a look at number 9 anyways. This one here?
Just the D's.
Okay, let me put the whole thing up and then we'll just take a piece of it. Okay, so number 9 in this assignment. All right, couple things. After the first bounce right here, the highest height after the first bounce is T2. After the second bounce, the highest height is T3, and so on. So that's going to be, because that's going to be a little tricky down later. And which letter did you say you had problems with?
D.
With the very last one?
Yeah.
Okay. So what is the general term here? What's the general term for this? What'd you get?
3.
T of n equals 3 times 0.75 to the power of n minus 1. Okay, so that's the general term. Everyone's good with that? Okay, so here's T1, 3 meters. That's right here, T1. 75% of its original height, so multiplied by 0.75 is the R. Okay? And so it says, after how many bounces will the ball reach a height of approximately 40 centimeters? So, okay, so 40 centimeters looks like it's going to be your height over here, right? Because remember, the T1, 2, 3, 4, 5, 6, 7, 8, 9, those are the heights. So 40 has got to be the nth term. We know this is 3. I know this is 0.75. We don't know what n is, right? So with this one right now, and for you guys, it's just going to be kind of trial and error, really. It's just going to be trial and error for you. We don't have, right now, you don't know of the exact way to get an exponent out of the, a variable out of the exponent position. That includes a concept called logarithms. If you want to look that up sometime, you can. It's a little more efficient. You can find exactly what you're looking for, finding a variable in the exponent position. But I don't think we're at logarithms yet for you guys. So for this question, all you need to do is sort of just do trial and error. Okay? Just check some things on your calculator. So 40 divided by 3, let's get rid of this 3 first. What's 40 divided by 3? Somebody grab that? What'd you get? 13.3, repeating, okay. So now I need to figure out sort of how many times, right? Points, okay. So 40 centimeters, is something wrong here? Something's wrong here, okay. So this is 40 centimeters, but this is 3 meters. Is that right? Okay, so we got an issue here. This nth term formula is in meters. This 40 is centimeters. So what we have to do is either write this 40 as 0.40 to go with the meters, or we have to write the 3 meters as 300. Right? So that means that this is actually going to be 0.13333. Does that make sense? Does that sound right? Okay. So we have to use this number. Okay. Do you know why I paused there? Because 0.75 times itself is only going to get smaller. It's never going to go up to 13. So something was wrong there. And maybe you recognize stuff like that. All right. So in order to find n, you have to figure out what exponent you're going to take 0.75 to get 0.1333. So all you do is you just kind of guess. So that's no problem. So you go 0.75 to the power of, now we can deal with n a little bit later. Let's just see what power is going to get us close to this. So what about 6? Oh, that's pretty close. 0.17797. What if we went to one more and got that down a little bit more? How close would we be there? So 0.75 to the power of 7. What does that give us? Oh, look at that. Okay? I know. Ooh, isn't that great? That's so exciting. Okay, so it looks like n minus 1 is actually 7. So this is important. N isn't 7, but n minus 1 is approximately 7. Now they put a little dot up there, it means approximately. So n equals approximately 8. So you'd probably say after the 8th bounce, so it's 8 down here, gives us, the 8th position there. So after the 7th bounce, the 8th position. Is that what the back of the book says there for D? Is that what our solution is? Okay. I have no idea. I'm trying to work through this like you guys would work through this. So I'm trying not to have everything in front of me here, okay? So any questions? Okay. All right, so we have Pre-Calculus 20 in the McGraw-Hill Ryerson Pre-Calculus 11 textbook here. You can join me on page 46 if you have it. That's where we start here. And geometric series. Now, this is pretty logical. I think you were probably expecting this, right? Because we did arithmetic sequences. Then we did arithmetic series. Then we did geometric sequences. And now we're doing geometric series. So I don't have to kind of go through the concept of what a series is, right? You should kind of already know that. So what we're going to do is we're going to talk about a geometric sequence just really quickly again to review that. And then we're going to basically kind of skip forward to the formula for the geometric series. There is a derivation of this formula that I could go over with you. It's in the textbook. I'll just briefly highlight it. I'm not going to go through it with you too in depth because honestly, you don't really have to remember how to do that. Some of you would find that interesting. Some of you might help you understand that a bit better. But I think most of you will probably get lost in this derivation and be like, what just happened there? So I'm not going to go over it. If you guys want to look at it, you can. If you want to ask me about it, love to spend some time with you on it. But a geometric series, of course, is the sum of all of the numbers in a geometric sequence, right? So a geometric sequence, as we just went over in our last section, is a list of numbers, and each number is separated by a common ratio, right? So we multiply a number by the ratio to get the next number, then by the same ratio to get the number after that, and so on. So that's geometric. Arithmetic we add, geometric we multiply. Okay? So the geometric series would be the numbers in a geometric sequence all added together. So that's what we're doing. So we're going to come up with the formula for that, and I think it's kind of neat to mention this. I'm not going to go through this investigation, but do you guys know what a fractal is, or a fractal tree? Have you ever heard of that? Fractals. So what happens is in a fractal tree, this is a fractal tree, and you may have seen something like this before, but if you take a look at a small piece of it, the smallest piece of it, it actually mimics the largest piece. So look at this. This is kind of like a tree with two main branches there. Two main branches. Well, if you move along like from this stem right here, this is like a tree with two main branches. And then if you kind of keep going on, this is like a little tree with two main branches. And then this is a little tree with two main branches. And then this is a little tree with two main branches. And then it keeps going on. So the larger bit is made up of a whole bunch of smaller pieces that are the same. So it's like a repeated pattern that kind of like, yeah, I'm not explaining it very well. I'm trying to explain it in just everyday terms. But you can see the larger picture in each one of the small little bits in the picture. Okay, so it'd be like a repeated pattern. All right? Okay, well, anyways, again, if you want to study fractals, you can. That's a good thing for you to study. Watch a video on that, do some reading on that. Fractals are pretty interesting. And there's some pretty interesting artwork, too, that uses fractals. So, all right, so a geometric series, I have this clipped out into the notes here. It, of course, is the sum of all of the terms in a geometric sequence, and blah, 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 blah. Let's do an example that might help you to understand, where we might use a geometric series. So if a school district has an emergency fan-out system, or emergency phone tree is what we call it, it's designed to enable important information to reach the entire staff very quickly. So you've maybe seen something like this before. At the first level, the superintendent, who's kind of the boss of everybody, calls two people, okay, the two assistant superintendents. Each of the two assistant superintendents call two more people. They call the two principals. Then these four principals call their what's next, vice principals or whatever, the two other people. And it could keep going on indefinitely, right? This is sort of like a fractal, really, right? We have one person connecting with two. We have one person connecting with two. We have one person connecting with two. And this person, of course, would connect with two more, and so on. And so you kind of make this tree diagram a little bit, okay? So if you have, you could quickly find out how many staff you have by adding each row of this factor tree, or of this, emergency phone tree. And that would represent a sum of a geometric sequence, okay? So there's 15 people involved here. There's 1 plus 2 plus 4 plus 8. So because each person is calling two people, we know that each row grows by a factor of 2. This is a geometric sequence. Okay, 1, 2, 4, 8. So again, in the textbook, and I'll just go back and maybe just run over that real quickly. I'm not going to do this with you, but there is a way, sort of like Gauss did his method, right? Remember that Gauss's method from 1.1? Sort of similar to trying to find patterns here, and then using the common ratio, using different things like that, maybe the first term. And so when you do this, and you see, this is why I'm not going to go over it with you, because I don't want you to get too lost in this. But there are two important versions of a sum formula for a geometric series that we're going to study. And it all kind of boils down to this one right here, okay? And so that's the one that I have clipped out. So let's just take a look at that. You might want to write this out in your notes. It is in your textbook. You might want to jot this out in your notes and make sure that we understand what everything represents here. So again, this is S of n. That is the sum of the first n terms in a geometric series. So the first n terms. And you find that sum by multiplying the first term by r to the power of n. Okay, so r is the ratio. You have to know the ratio. To the power of n, so it's the same n as the number of terms here. And then you subtract 1 from that. And then you divide that by the ratio minus 1. So remember, r is the ratio. Okay, so you don't need to know the last term in any, like in this at all. So that's kind of nice. So we can do an example like example 1. So when you're done kind of writing this down, oh, I should talk about this too actually. R cannot equal 1. Can anyone explain to me, or do you know why r, the ratio, cannot equal 1? It doesn't work here. Anybody know? Or yeah. Okay, good. Yeah, r. Okay, so if you look at the formula here, if r was 1, you would have to divide by 0. Perfect. Yeah, awesome. That is absolutely true. Now, it wouldn't be much of a geometric series either if the ratio was 1, because it would be whatever number you have first, it would be the same number. The list would be the same number. And so technically, I would say that that's not a geometric sequence. Even though you have a list of all the same number, you could say, hey, Mr. Maxwell, the ratio is 1. But why is it not an arithmetic sequence with the difference being 0, let's say? So if something can be described as both an arithmetic and geometric sequence, I'm not really sure that it's either. So you might find some math teachers that will be willing to debate you on this, so whether it's one or the other or neither. I'm not going to get into that. I don't really know what I believe yet, but I might have to look into that. It's going to be important for me to know. Probably for all of us teachers to know. Because I'm sure some kid's going to ask you, is the list of 1, 1, 1 indefinitely arithmetic or geometric? Is that? Like, I need to know this. So we need to be ready for that question. I know all you students are going, okay, what just happened? Oh, this sounds really lame. Okay, so example 1. Let's get to example 1. Determine the sum of the first 10 terms of each geometric series. The first 10. So, what do I know? I know that n is 10. Okay? What is r? Can I find r here? Well, r is going to be any term divided by the term before it. So it looks like r is 3. Does that make sense? 4 times 3 is 12. 12 times 3 is 36, and then so on. Does that make sense? Okay. So I've got n, I've got r. What else do I need? Well, let's go back and look at that formula again. I'm going to need T1, right? I need n, I need r, I need T1. Good job. So T1 is 4. So the sum of the first 10 terms looks like this. 4 times r is 3 to the power of n, which is 10. And then I'm going to subtract 1. Please don't, this is not the same as 3 to the power of 9, right? You got that? You understand that? It's not the same as 3 to the power of 9. You got to do 3 to the power of 10 first, and then subtract 1 from that. Divided by r minus 1. Okay, so that's how you put everything into that formula. So let's see. The sum of the first 10 terms is 4 times, what's 3 to the power of 10? That looks like that's going to be a pretty big number, isn't it? Maybe too big for us. Oh no, that's not bad. 3 to the power of 10, 59,049. So 59,049 minus 1 all over 2. All right, so the sum of the first 10 terms is 118,096. Any questions about that one? Example 1? All right, example 2. Okay, determine the sum of each geometric series. So I have T of 1 is 1 over 27. I have, what else do I have? I could find R. So what is r? R is 1/9 divided by 1/27. Ooh, that's 1/9 times 27/1. 27/9 is 3. So the ratio is 3. You multiply each term by 3 to get the next term. What about n? What's n? N is not given, and all these dots don't really help. I can't really count, right? I can't really count that. So you have to find n first. So this is where we go back to the geometric sequence, the nth term formula, and we calculate for n. So who remembers what that is? T of n is what? From last section, anybody remember? T of 1 times r to the n minus 1, is that right? Okay, that's the nth term formula. So I know T of n, 729. I know T of 1, it's given, 127. I know r is 3. And then I have n minus 1. Okay? Okay, so when you get the 27 off of this side, and you end up with an equation like this by multiplying both sides by 27. So really you can just do trial and error here now, like 3 to the power of, well, 10, what's that? Oh, that's quite a bit. So that's quite a bit more, right? So that's no good. 3 to the power of, let's say 6, what's that? Oh, that's 729. Oh, that was this one. So let's keep going. 3 to the power of 8. Oh, getting close. Actually, if you just keep going times 3, that's like 3 to the power of 9. See that? 3 to the power of 8 times 3. So let's just check that. 3 to the power of 9 is 19,683. There we go. We got it. So what does that mean? This is 3 to the power of 9, and that equals 3 to the power of n minus 1. So 9 equals n minus 1, and that means n is what? 10. Okay? So now we've solved what n is, and now we've got everything we need. We've got everything we need for the sum formula. Okay, so the sum of the first n terms is, what's that formula again? T of 1, which is 1/27 times 3 to the power of, oops, I guess I can write this as 10, guys, sorry. Write that as 10, sum of the first 10 terms, because I know this is 10. Minus 1, all over 1/27. Oops, nope, that's the first term. R is 3. 3 minus 1. So we have a lot of fractions here, right? Rationals. So this might not be a whole number. We got to understand that. So let's do 1/27. 3 to the power of 10 minus 1. It's 59,048 from the last question. All divided by 2. Right? So a couple things you want to remember. Again, I'm not sure how. I'm not sure what the math skills are at here, where you guys are at just yet. But remember that you want to probably evaluate the top first and then divide by the bottom. There's different ways you could do this, right? There's different ways you could do this, but I would probably multiply this first and then divide by 2. You could do this. You could actually view this as, like, divided by 2 could be the same as multiplying by 1/2, right? You could do that as well. So then you could do these two first. And it's 1/54, right, times this big number. So whatever you want to do, however you want to do it, and I'm okay if you write it as a decimal here. So evaluate that and make sure you can get the correct answer. Okay? So let's see what we got here. This divided by 54. So does this look about right here? Where are we? 1093, yeah, 0.48. Okay. All right, so I'm okay with decimals here, even though there's fractions in the question. This is fine for this one. So as long as you can get to something like that, okay? And your calculator would be able to give you a lowest fraction, a reduced fraction too. So, okay. So that is example 2. So finally, in this lesson here, the key ideas. A geometric series is basically the sum of a geometric sequence. Just like we talked about, here's the formula. R cannot be 1, and then this formula holds true. And this is the sum formula as well. This is a variation of the sum formula. If you know the, let's see, if you know the final term, you can actually use this one. So this is the one last thing I'll add to the lesson. A variation of the formula can be used when the first term, the common ratio, and the final term are known. So you can use this one when you have the final term. So this would be a good one to write down as well. We'll mostly be using this one, but this one is good as well if you know the nth term. Okay? All right, which in that in one of those examples, I guess in this one, you see how we found n, right? In this example, there is a bit of a shorter way to do this one because you do know the last term. So if you know t of n, which we do in this one, you could have used this second formula right here. Okay? And that actually might save you a bit of time. So write this one down as well. This is what you use if you know the final term as well. Okay? So your 1.4 assignment.